Here we go, scholars. Let's rock this lesson. The last lesson of our stats unit. Do you guys have your calculators out? You're not going to need them as much as you think you do on this lesson, but we should always have our calculators out from when we are working with this. But I also want to make sure that you guys are ready to work with some stuff. Okay, let's do a quick review, okay? Let's just see if we can remember a few things. What if I did a histogram that kind of looked like this? And boy, make my ear histogram. You don't have to draw this out, guys. How would you describe that histogram? By the way, sloppy would be the number one thing you'd describe it with. But what shape would you describe that? Skewed. Which way? That's left skewed. Okay. Now, if you have skewed, and I'm going to do a right skewed here real quick. Let's do one that looks like this. A right skewed. What do we use to measure its center? What do we use to measure the center of skewed? Yeah. The 5-number summary. So what's the center of a 5-number summary? The median. So we used our median, right, to describe it. So we knew median. But then we have, when we look at histograms, we might have something that looks like this. Now, how would you describe that histogram? What do we say? Roughly symmetric. So we were like, okay, that's relatively or roughly symmetric. But how else do we describe that shape? Bell shape. What do we call something that's bell shaped? Oh, so we're using a normal distribution, okay? So that's when we're going to have the bell shape. What do we use to describe the center of a bell shape? We use the mean. What do we use to describe the spread? Standard deviation, okay? So we've been working mainly with normally distributed stuff. So today is another day of the normal distribution, okay? So when your data is normally distributed, so we know it's symmetric, right? And it has that bell shape, we can make informed decisions about probabilities. Now, I want you people look at this like, oh no, probabilities. We've been doing this the whole time. When we talked about the normal curve before, what did we use to describe it when we're looking at it, especially for the empirical rule? What do we draw when we're doing the normal distributions? What do we put the mean in the middle, then what, my friends? Isn't this our 1 standard deviation out? Our 2 standard deviation out? Our 3 standard deviation out? Are you guys with me? Okay, and what do we know about those? Between my first, basically, 1 standard deviation away from the mean on either side is what % of our data? What's the probability that a piece of data is going to land between 1 standard deviation? Thank you. Now we're just, instead of talking percentages, we're talking probability, which uses our what? Percentages. Do you see where we're going today? It's not going to be that because we've already been naturally doing that. Okay, let's do another quick review. Going from here to here. If I'm 2 standard deviations, either above or below, how much of my data is in there? 95%. What's the probability that data is going to land between 2 standard deviations? 95%. Do you see how they're trying to make this more complicated, but it's really not that complicated? And then we get our last one. How about 3 standard deviations away from the mean? What's the probability that I'm going to land my data is going to land in there? Yeah, 99.7%. Guys, that is going to be your empirical rule, right? Where most of our data lands between 3 standard deviations of those. So, we're literally going straight into examples, all right? There's nothing really new that you learned. So let's read this through. And here's the part you probably have detested this whole time in statistics. I don't know if this is true. All the reading, right? The little details. It is, for a lot of you, like, it doesn't feel like math because I'm reading so much, right? That's geometry too. We do a lot of reading to set up problems. So let's read this one. This is modeling blood pressure with a normal distribution. So suppose a study tracked the diastolic blood pressure of 40,000 participants. The results show that the blood pressure measurements were normally distributed with a mean of 80 milligrams, of mercury? 80 milligrams of mercury, and a standard deviation of 10 millimeters of mercury, which is 1 unit used to measure pressure. So you guys know on the blood pressure cuffs, you guys with me on that? And you always see those going up or down. There's two different types of cuffs. You have the one that has like the wheel, you guys with me on that? Or you have the one that has the mercury, where they watch it, you just watch this thing go up. It's weird. Those matters what doctor's office you're on. Now they just put electronic on you. It's easier. But there's a mercury one, the good old days. When I was a kid, the mercury literally looked like almost like a thermometer where it would just go up or down based off of your blood pressure. So just know that's where they're getting the idea of mercury, working with it. Now, work with what you guys are thinking here. It says, complete the diagram using what you know about normally distributed data. Fill each box under, this is where directions come in, under the horizontal axis with the appropriate measure of pressure. Are you guys with me on this? Okay. So when you were working with this, guys, what would go right here on the bottom? What goes right? It's the mean, right? Well, what's the mean that they told us? Yeah, this is going to be our 80 millimeters of mercury. So it's 80 of that, okay? So that's our mean, our X bar. Okay, what did they tell you your standard deviation was? 10, right? And by the way, what's standard deviation again? The average distance from the what? The mean, right? It's the distance away from the mean. So if it's 10, what's going to be our first value over here? 90 milliliters of mercury. And then we have 100 millimeters of mercury. And then we'd end up having our 110 millimeters of mercury. All right, because that's your 1 standard deviation, 2 standard deviations, or 3 standard deviations. So we've done the positive side, and now we need to go to the left instead. So then we just have to do the same thing, but subtract 10. So we have 70 millimeters of mercury, which is 1 standard deviation to the left. Then we have our 2 standard deviations away from our mean, which is going to be 60 millimeters of mercury. And then we have our last one, which is going to be 50 millimeters of mercury. Okay. So far, makes pretty much sense, correct? Now, I want you to think a little bit more of this. So we filled the first part in with the appropriate measure pressure. Then it says the following. Then fill in each box representing an area under the normal curve with the approximate number of people you would expect to find in that region of the graph. Okay? So I just want to know how many people would land there. Well, let's think about this for a moment. Guys, what is from here to here? What percent? 60. So we know how much is here. 34. Would you guys agree? It used to be 34%. Okay. How do I find out the number of people here? Is this any different than what we've done before? How do we find out the number of people? 40,000. Yep. 40,000 times what? 0.34, right? So by our percent. So we change that. Well, guys, where's your little calculators? What's 40,000? 34% of 40,000 real quick. What do we get? All right, so it's 13,600 people. Now, do we have to recreate the wheel? No. If we know that it's 13,600 people from the mean to the first standard deviation on the right, is it going to be that many on the other side? Yes, we totally would agree that would be the case. So this is 13,600 people. All right, now, quick question. How do I find the amount of people here? How do I find the amount that goes on either one of these next boxes? Yeah. Okay, and then do what though? Because this goes from here to here. I agree with you. You could do it that way. Did you hear what CJ said? He goes, find 47.5% up. Did I do my math right? 95%, right? 47.5, yes. Okay, 47.5%, which would be how much? From here to what? There. Could we do it that way? Or is there another way we can do it? Because you're right. You just have to subtract your 13,600 people. What's another way we can do it?
I was going to say, like, subtract 68 from, like, 95, and then, like, take half of that.
Yeah, you can totally do that. So we got 95 minus 68. What do we get there, guys? Isn't that 27? Would you guys agree with me? My math isn't totally off today, is it? 27. And then what do we do to it? So that means this and this adds up to what percent? 27%. Divide it by 2. What do we have? 13.5 what? Percent on both sides. Now, do you see how you would still get it, CJ, though, if you go the way we discussed? Yes. So now can we just do the same thing here? What is 40,000 times 0.135? All right, someone punch that into their calculator real quick, and what do we get? All right, so we get 5,400. Notice we're still labeling it, people. Which, by the way, doesn't that mean it has to be the same thing on the other side? All right, so we got 5,400 people. All right, friends, you know we can get the next part. How are we going to get the next ones? How in the world, blue here, are we going to get the ones that's between the third and the second standard deviation? So here's my second, my third standard deviation. I want to figure out how many people are there. What percent of the graph is that? Can we use the same type of idea that we did before? Yeah, guys, can't we go here? What is a way of doing this? Can we go 99.7 minus what? 95, right? Would you guys agree with me? So 95. And we get here 2.7%. Well, that's from here to here, and from here to here, better add up to 2.7%. What's half of that? Did I see 2.7%? Did I get that right? Did I just do my math wrong? It's 95, the other 99.7. It should be 2%, right? Should be 4. Oh, yes, thank you. That's why I'm like, why is my math not working? Thank you. Love it when my mind doesn't work great. Wonderful recording it so the whole world knows. Yeah. All right. So when we are working with it, it should be 0.3. Someone go wrong. Isn't it 40? Someone do the math for me real quick. What's 99.7 minus 95? Okay. All right. Divide by 2 should be 2 point what? Thank you very much. 2.35%. Perfect. When my math does not work right, I feel for you guys. All right. This is why you shouldn't trust my head. Okay. Going on. Now, how do I find out how many people are there? Can we just do our 40,000 times that as well? So on this one, we're just going to go, okay, I got my 40,000 times 0.0235, which is going to give us how many people? Should be 900, right? Should be 940 people. Okay, so 940 people. All right, now there's 2 different ways you can get the last one. What is one way that I could actually get the last number, the last box for the number of people? What is one way we could do that? Yeah, Ava. We could literally go 100 minus 99.7, which we all know makes what? What percent is on the outside of my 3 standard deviations? 0.3. So do you agree with me that this value right here is 0.15%? This would be 0.15%. Would you guys agree? And then what's 0.15% of 40,000? It should be a small group. Yeah. And we know it would be the same on both sides. So you make it readable. So 60 people on both sides. Now, what should all these people add up to? 40,000. And the percent. If I was adding up all those percents, should it equal 100%? Yeah, because then we know that we have our normal distribution. So really, is this any different than what we've already been doing? Huh, not really. All right, so let's go ahead and let's apply this stuff here. Now notice they ask for probability, but if we understand percentages, it's really simple. It says, what is the probability that a randomly selected person from the study had a diastolic blood pressure higher than 80 millimeters of mercury? Is this greater than, less than, or equal to the probability that the random selected person from the study had a diastolic blood pressure lower than 80 millimeters of mercury? Explain your answer. Well, guys, let's use our probability notation. So we're looking, what's the probability that I'm going to have a blood pressure greater than 80 milliliters of mercury? Now, you could do this 2 different ways, okay? Most people would be like this. Okay, Gregerson, we know there's 40,000 people. And what do we know about how many people are going to be to the right? That which is greater than. Hello? Greater than 80 milligrams. How many people should that be? If we're normally distributed. 20,000, right? Because it's half of it. So it's 20,000. Guys, we know that's 1/2 or 0.5, okay? Or what percent? Or 50%. By the way, when we talked about normal distribution before, what did we say? Everything above the mean is in 50% of the data. Notice nothing changed. We just call it probability now. Same type of stuff that we did. Now, they asked the next one. We want to compare it to the fact it's less than the diastolic blood pressure of 80 millimeters of mercury. Isn't that the exact same thing? Oh yeah, they're what to each other? Yeah, they're symmetric, so they are equal to each other. So it's going to be equal. Which makes sense because a normal distribution is symmetrical. Now remember, when we say something's normally distributed, if they don't give you the histogram, we get to use the fact that everything's about that amount. It's not always 100% certain, but for what they told us, we get to use this to model the data. All right, now let's have a little bit of fun and see if you guys got this. See if you remember the good old days, because I don't think this is anything different than what you already have. And here's the thing. I think you can make it easier than harder. I'm showing the hard way, to be honest with you right now. Okay? Because look at the next question. It says, what's the probability that a randomly selected person from the study has a diastolic blood pressure between 70 and 90 millimeters of mercury? Guys, 70 and 90. Where do those land on our normal distribution? That's our 68%, right? Like most of us know, and I'm just going to write it down here, the probability of being between 70 and 90 millimeters of mercury, you should know is just what? 68%. That's the probability. Now, what if I said, show me the math? Well, to show me the math, wouldn't you just go like this? 13,600 plus 13,600 divided by what? 40,000. But if we know the empirical rule, do we have the probability already down? I love it when it's easy. So notice today they're trying to make it harder than it really is. If you know your empirical rule, you know the probability already of this working. Okay, let's look at the next one. What is the probability that a random selected person from the study has a diastolic blood pressure between 60 and 100 millimeters of mercury? Guys, 60 to 100. Where do those land? 2 standard deviations, right? Guys, you should be able to tell me the probability without even thinking. The probability of being between 60 and 100 millimeters of mercury. Those are 2 standard deviations. What's the probability I'm going to be between there? Yeah, that's going to be 95 what? %. Why? Because on our normal distribution curve, we know between 2 standard deviations above and below is 95% of our data. So the cool thing is, what if I said, oh, show me the work? Well, how would you show the work? Well, if I said, show me the fraction, there's the easy part. We'd have 40,000, and when we just add them all up together, you really have your 5,400 plus your 13,600. Sorry, I'm making that really small. Plus your 13,600 plus 5,400. Would you guys agree is what you would do for the work? But the cool thing is, if you know the empirical rule, do you already know the probability? This is what I'm trying to get to. We know the empirical rules. Do we know probabilities? Yep, because probability can be written as percentages. It's as simple as that. All right, what's the next one? What's the probability that a randomly selected person from the study has a diastolic blood pressure between 50 and 110 milligrams of mercury? Now, guys, again, should we know this without having to think too hard about it? So the probability of being between 50 and 110 milligrams of mercury. Okay, talk to me. What do you guys know? Probably this is so easy. What are you going to tell me? Yeah, it's your 99.7%. Like, what would be the work? Well, the work is your 40,000. And when it, okay, this is the slacker way of doing the work. Isn't it everything but 120 of the people? Yeah, so couldn't we just go like this? 40,000 minus 120 to make that really easy. If I said, show me the fraction, that's what you'd have to show me. But if I just said, what's the probability, and I told you it was normally distributed, and you know what your probability of being between 3 standard deviations, great. That's how easy it's supposed to be. Now, it says here, well, how are they related to the empirical rule? They're what? They are the same. Would you guys agree with me on that? They're equal. We know the empirical rules, percentages, is really going to give us the probability for that data. Simple as that. Don't you love how it works? They are the same, I should probably do this, as the empirical rule. All right, now that you've seen how easy this is, do you see where we're going with the next problem? Okay. So let's do the exact same type of idea. We're going to do this with women's shoe size, okay? Why don't they use guys' shoe size? I don't understand. But anyway, they're going to use women's shoe size for this example. Let's read what it says. It says, do you know that women's shoe sizes can be modeled by a normal distribution? In the United States, the mean women's shoe size is 8, with a standard deviation of 1.5. Use the information to answer the questions below. Now, here's the weird thing about shoe size. You know how we always put the label at the end? Do you describe shoes like 8 size? No, we write it as how? Size 8. And it's annoying. Like, it's a one-time, like, let's do an example and let's make the labels weird. Okay, when we're working with this. But should we be able to quickly be able to work with it? So let's go with the next one. It says, complete the diagram of the normal curve using the information from the shoe size scenario. Fill in each box under the horizontal axis with the appropriate shoe size. All right, guys, go ahead and fill those in. But just know the label goes in front when you're doing this. So this would be size what? 8. And that is going to end up being your mean. Go ahead and fill in the other sizes based off of using your standard deviation. All right, should be able to have this down pretty quickly. Guys, what is going to be a positive 1 standard deviation? Size what? 9.5. Make my 9s look a little better. 9.5. All right, so what's our 2 standard deviation size? Positive standard. 11. And then we have our size. Shouldn't this would be 12.5? Is that right? Yeah, 12.5. Okay, make sure my math is adding correctly. All right, now going backwards, we're at negative 1 standard deviation. What would we have? Size what? Yep, 6.5. And then what is 2 negative standard deviations away from the mean? 5. And then the smallest feet out there probably would be size what? 3.5. If the shoe size gets down to that, if you go to a shoe store, gentlemen, just so you know, you wouldn't find a size 3.5 for women's shoes. Girls, where would we go shopping? Kids section at that point, just so you know. 5 is like the lowest they really ever go. But anyway, just so for shopping, that you probably don't care about at all. But just no. All right, now let's look at the next one. It says, then fill in each box representing an area under the normal curve with the probability that a randomly selected woman in the United States has a shoe size in that region of the graph. Now, guys, this is just the percent, not the number of women. Are you guys with me on this? So when we work with this, is this going to change anything from what we did the last graph, basically? No, because we know this is going to be 0.34 or what? 34%. This is going to be 0.34 or 34%. Oh, wait. Oh, that's my 68% rule right there of my empirical rule. Now, using what we did on the other one, we know this is going to be our 47.5, which leaves this to be 0.135 or what? 13.5%. And that goes both places. All right, so far so good. Okay, what do we find for that next percent that we were going to have? This is going to be 0. What? 235, is that right? I got my values right on there. And so we got our 0.0235 or 2.35% or 2.35%. Again, decimals and percents, we've got to be very comfortable with working with all of them. And then guys, everyone knows this by now. What's the percent with the empirical rule when you're outside of 3 standard deviations? On one side, it's going to be what? 0.00, right? 15. And 0.0015, where it's going to be 0.15% and 0.15%. Now guys, are we surprised by any of this? No, we know the empirical rule, so we should be able to work with it carefully. Now, let's look at these on the following. This is literally how easy it is to show work on some of these. You've got to use your probability notation, an improvement that needs to be made by most people and not everyone, okay? It says, what is the probability that a randomly selected woman in the United States has a shoe size between 6.5 and 8, okay? So the probability of between size 6.5 and size 8. Guys, what is that going to be? 0. What? 34 or? Gotta love math sometimes. Gotta love it when it works out nice. Pretty simple? What do you guys think so far? Easy schmeezy? All right, how about the next one? What's the probability that a randomly selected woman in the United States has a shoe size less than 6.5? Explain how you determine your answer. Okay, now we're doing verbal explanations. We should be writing these down, but we're doing verbal today. First of all, let's write what is down. We want the probability that's less than size 6.5. Okay, talk to me. How would I get this answer? Dan, what were your instincts telling me? How would I get this answer? Make it easy. Don't make it hard. All right, so we have the 13.5% right. So I'm just going to go 0.135. Is that the only one? Right? Keep going, don't I? Because this just goes from here to here, the 13.5, and this is just less than 6.5. So do I have to include everything that's going that direction? All right, so Sam, what are my other values then? Plus what? Yep. Yep. That's what I want to hear. All right, and then we just add those three percentages together, and we're going to get here. Was it 0.16? Someone double check it on their calculator for me, please. Is that what I got? Oh, thank you very much. Or we'd say 16%. Okay, so 16% of the women in the United States, their shoe size would be expected to be below 6.5. So this would be your work. Are you guys okay with that? I know it's rough, but you think you guys got the work down for that? Good. All right, let's look at the next one. I think you guys are starting to get used to my sarcasm. I think you're starting to read it pretty well sometimes. I need to have caffeine in here for something for you guys or something. I don't know. I gotta get you a little more energy, people. All right. I know it's Monday morning though, so it's harder. Now, what's the next one? What's the probability that a randomly selected woman in the United States has a shoe size greater than 6.5? So I want the probability of being greater than size 6.5. Okay, guys, if we're doing this, there's two different approaches that you do with this, and it's great. If you've had the previous problem was part of it, you have a quick, easy way. But if you didn't have the previous problem, how would you figure out the probability for this? See? Yes. Yeah. Greater than, remember, you're always, greater than, the opening is always to the left. So it does matter here that I'm going to be bigger than size 6.5. You could write the word out if you're uncertain about the symbol. I would too. Normally, you would sit there. You could also write it this way, which I wouldn't love. You could go size 6.5. No, I think we're going to need to go. Did I just put, oh, I did this one the wrong way. Guys, why didn't you tell me earlier? Now I'm feeling better. Okay, greater than 6.5. You could also just use the words probability of greater than. Because some of you are uncertain of your inequalities, so size 6.5. You could also do that. I'm good either way. As long as you have your probability notation, which needs to improve. Okay, guys, what are we going to do? What's the easy schmeezy part we do with this? Can we just add the probabilities? Yeah, because I'm just going everything, what? This direction, basically, is what I have to add. So when we have this, we got 0.34 plus 0.34 plus what? Yeah, 135 plus 0.0235 plus what? 0.0015. Again, basically, I'm just adding up what all that whole percentage is, which is what, my friends? What did we get for that? .84, correct? Which is what percent? 84%. Now, here's how we would have done it before. How many of you go like, oh, half of this is 50%? I add what to it? 34% gives us what? Notice we're doing the exact same thing that we did before. Yes, question.
Well, I was just gonna comment. What I did is I did 100 minus 16.
And that's what's going to be my next thing. Yes. Guys, if we know, like I said, if we knew the previous answer, don't we know the exact opposite is just 100 minus that? So another way you could have done this, as long as you showed your work, you could literally go 100 minus 60. Now, we're doing percents when we do this. That would have given you what? 84%. Yes, sir. Yes. All right, are you guys good with this so far? What do you think for the last lesson? A lot nicer than some of the other ones? Yeah, me too. I agree. All right, next one. It says, what is the probability that a randomly selected woman in the United States has a shoe size between 9.5 and 11? All right, let's write this down and then you guys are free to go. What's the probability of between 9.5 and, between size 9.5 and size 11?
The following students,
What do
please
you guys
stop by
think?
the front office. Will, Angel, Grace, Paul,
Isn't it
Rita
this value?
Ramirez, please stop by the front office.
And when you look up above, would you guys agree? It says between 9.5 and 11. It's just what? 13.5? All right. You see how easy homework's going to be tonight? Start working on your quiz corrections. I'm available at lunch day if you want to come work on them, okay? And after school. All right. Good job today, guys.